because that's what my middle name is. Yeah. I really don't. Oh, there we go. Now I hear myself. All right, welcome. This is basic antennas, and few people have seen how this demonstration is done. How many people have not seen this before? Good. Okay, excellent. I don't use the screen. I'm the backboard, and this is where everything happens, okay? So basically, for those that have not seen this event, or talk, or demonstration, whatever you want to call it, it's a very visual, non-electronic, except for the fact that we got a radio, demonstration. And what it does is it shows antenna patterns and how radio systems work, and to improve the output of your antenna system. So what we're going to do here is we're going to build a 3-element Yagi. That's what's up on here. And we're also going to do an omnidirectional and show you how the ground plane changes the characteristics of a vertical antenna. Okay? And what we do is very scientific. So I hope everybody brought their calculators and sketch pads and all of that. Nah. Yes, I do. As a matter of fact, I have 2 of them. And you know where they are? They're in the back of one of the drawers of my desk at home. So what I do is with this talk is I show through the use of bulbs the strength of the signal. Okay? So that's what I mean by it's very visual. So you'll see the RF pattern as it's put out from the antennas as we go along from a basic dipole antenna and build upon that to make the Yagi, and how the pattern changes as each element is put on and all of that. So that's what this talk is all about. Now, anybody want to give it? No? Okay. Again, very simple. I first heard of this talk when, a year after I got licensed, a gentleman by the name of Norm Greenberg gave the talk, and it was out at Suffolk County Community College, and I was so impressed by it that it got some of the thought processes working, and I said, you know, that's great. So the following year I came back with my video camera and I recorded it. A couple of years after that, Norm passed away, became a silent key. And it took me about 8 years after that when I said, okay, do I have the cojones to do this? And I put it together and was surprised by how it worked out. Norm did a lot more with a couple of other forms of antennas and demonstrations and stuff, but I think I talk a little too much before and afterwards, so to do all that. But still, it goes on. I've given the talk all across the tri-state area, and at different local radio clubs and all, and it's I'm proud to say that a lot of people have enjoyed it, and a lot of people have talked about it, and then as they've got into the Elmer stage, you gotta go see Walter's talk. So thank you for being here today for that, and all that. So basically it's real simple, and what I do is let that sit there. The whole structure of the antenna is so simple it's ridiculous, and this is nothing more than a light tripod, light stanchion. Everybody knows that anybody that's in construction, 1x2 furring strip, fuse holders with the clips bent down. This is just a little piece of aluminum with a hole drilled in it to receive the SO239. So that'll sit up on there for the later demonstration. The elements is one with an SO239 piece of coat hanger, and the others are just alligator clips And then we come down to the brass tacks of the Yagi, which you can see in your tech class manual, and this is exactly how everything is. Created two dipoles. One is on a piece of block of wood, and you can see a separation in between the copper rods, so that way you've got your two sides. And the other one just sits same way. It's two pieces of copper, and it's just held together literally by tape. So what happens is we put this here, so that way the clips, come on, stop going down. There we go. When you hear the snap, it's in. So this is your basic dipole antenna, and what happens is you've got a positive, negative side. One side goes to your feed line, which is the center, and the other side goes to your come on, just 1 second. And the other side goes to your shield. So that's what makes up your dipole. Very basic, very simple. And when you transmit, it transmits to the fact, let's see, hopefully we won't have problems with the microphone. Oh, look at that. I would pick the one that has the bad bulb in it. I just noticed it because it's black. Oh, even worse than that. Guess what? We have to do a repair. Hold on 1 second. See, the one wire popped off. Yes, we have the home. Huh? Sure. Okay. Reason why it's so bright, right, is because it's a balanced antenna, dipole. Half of the antenna is going to the counterpore side, half of it's going to its transmitting side. So basically what occurs is you get all of the energy that comes out of your radio through its feed line system to the antenna. And since both sides are the same in length, it's balanced. Okay? The fact that it's also at 180 degrees from each other, and side to side, back to back, they don't interfere with each other. Okay? So what happens? Now here comes the fun part. What we're going to do is we're going to show you that as the RF is transmitted, it will. Yes. Well, I am trying to use the lowest Huh? Well, it's not so much as having a better idea. It's sometimes the idea is. Okay. Part of what goes on is as you transmit. Look at this, it's looking for another bulb. As I said, we have bulbs. Nah. Still a Boy Scout? Once a Boy Scout, always a Boy Scout. Okay, there you go. And this is on extremely low power. But you see, when it's not in the same plane, it doesn't light. Okay? Alright? Turn off the end. We're on extremely low power right now. And you can see it on the other. So if we would keep the same distance going around, you can see that a dipole does transmit energy, RF, in a circular pattern around the material that you use, whether it be copper rod, whether it be a wire, or whatever else. Doesn't shoot too much to the ends, and whatever you put into it comes out of it. The only loss that you'll have is what the feed line, in this case it's coax, is being used. Okay? It's great. You put it up, simple, easy. If you use wire, you can go in anywhere. And I'm not using the microphone. Thank you for the heads up. All right. What happens is with the pattern that you set up with the dipole, that's all you get. You get no gain. You get no directional pattern. So there's a couple different things you can do, and as if you remember in your tech manual, it talks about the Yagi, 3-element Yagi, which is what we got here. And we've got two other elements that are here. We have a reflector and we have a director besides the driven element. So roughly a quarter wavelength away, if we were to put in a reflector, and all we're doing is we're just clipping it into the mass. Notice it's one piece of material. Okay? So what happens is your reflector is now going to take this energy that's being transmitted universally around your element, and it's going to send it in all directions. But when it sees the reflector, it's going to look at this and it's going to say, hey, this is slightly larger in its frequency response, in other words, in its length also, that of the frequency that I'm using. So what it's going to do is go, whoa, stop. It's going to play traffic cop. And it's going to say, you don't want to come this way. I am not a resonant frequency that you can use. As a matter of fact, I'm something that's not in the area that you want to be at. So turn around and go back. So that RF is going to go from our driven element to our reflector and then bounce back and will be 180 degrees out of phase from what's being sent from here to start off with our raw energy. So it's going to go here to here. So once that double travel will make it longer. And what that does is it will now increase some of the output of our antenna in this direction. It's 180 degrees in phase because it's a quarter wave and a quarter wave back. So it's like a half wave. Yeah. So as you've got your transmission of RF coming out, the time that it goes to reflector and then coming back, it's still in the same. So it adds up. That's why you get a little bit of gain. this is seeing energy coming out of here, plus the energy that's coming back from there. That's why you've got the gain.
No
Okay.
reflector, there's no split involved, so it's one piece.
That's correct. So now what happens is, as we come across, remember how I could barely make it to the end to have it lit before because of the low power? Well, now you can see that it's strong. And if you go to the back side, okay? So that's what's there. Okay? Now if I come up in front of it, right, you can see a little bit of a glow, but not a heck of a lot. Okay? Until you get close to the tip. Interesting, isn't it? Okay. Now what that does is it's an effective way of getting some gain on your signal. It also gives you directionality because you also don't have stuff to the sides. And until you get up close to it, you don't see much above it either. But there is very, very faint right there. Okay? So it is taking the energy and it's bouncing it back and fanning it out. Now the problem is, with this being wider, of a frequency range or longer also, you know, as the physical length of the element, everything comes this way and you're limited to just that. You can't pinpoint, you know, bring the signal down more to a pinpoint. It's still very broad. So what happens is you put a third element up there, and what this is your director. And through here, all right. Notice the front element now, how strong it is, as compared to where it's driven. Okay, the driven and how strong the director is. Got here, nothing behind it, and again. Now this is interesting here. Watch this. Remember your voltage and current wave points on the quarter wave? Well, that's what you're seeing right there. Let's show that before. Now it picks up.
Those will affect the element in the middle where the lights get dimmer.
Yeah. Do you know why?
Because you're affecting, no, I guess not.
Okay.
Affecting the wavelength.
Is this connected to my feed line?
Yeah.
So it's not being driven, the energy is not coming from it directly. So it is what type of element? It's called an inductance, but it's also a parasitic element. What is a parasite? It lifts off the energy of others. Okay? Hence the reason when you're told whenever you use something like an SWR meter or the analyzers and stuff, get away from metal. Don't be anywhere near metal because it will interact with it. Okay, and that's what you just saw. Because this is in the near field, so it's absorbing energy because it's needs the light bulb. Okay, there are different types of light bulbs that you can get on here. They can become very powerful and suck up a lot of power or very little. I'm just using 47, number 47 pilot bulb. Okay. Others I can do the whole, remember back, well, I don't know. Yeah, it's already remember the CB days. days. And back in the CB days, what they did was they used a light bulb as a dummy load for testing the radios and stuff with that. So it's pretty much the same thing that we're playing with here. But the capability of the light and the amount of energy that it uses, not abuses, but uses, is what is going to affect the demonstration or whatever goes on. So that's that. So this is basically your 3-element Yagi. And what happens is, it's fun to play and experiment with, because you can go with a reflector and a driven element, or you can go with the driven element and just directors. You saw how intense it was before, so let me put this down again, sorry. Okay. Now the problem is, the minute you move your reflector out of the equation, you're no longer as directional with an antenna. So you need the reflector to give you a higher efficiency or a higher Q of the energy coming out of the front of your antenna, or your front to back ratio, as it's also called. Yes, sir. It's the length of the antennas, of the elements. Okay, this is the driven element. This is experiment set up for 146.000. Okay, when you deal with the reflector, and I can show you right here. Wish I had 3 hands. Oh, I know what I can do. How's that? Okay, so there we go, and you can see this element is longer than the driven element. This is the same as this. Okay, that's why it works more efficiently, because they're both the same size. So this one's longer. This is the one that says I'm 146.000. This one is longer, about a quarter wavelength longer. And when it sees this, it says, no, I'm not resident on your frequency, so go back, and it sends it back. This one here is a quarter wave shorter and is shorter. So when you look at this element as compared to the driven element, you can see that it's shorter. All right? Okay. The whole reason is frequencies that you're dealing with have to deal with the length of the wire or the material that you're using to make the antenna, correct? So the longer it is, it means that it stops the energy from going past that point. So it's acting like a wall, all right? Or as Mike brought out before, a mirror. The shorter one is saying, okay, come over to me, I'm more of your frequency because of the energy that's been expended from this point to this point where the director is, okay? So that's why you see the 3 different sizes of elements on a 3-element Yagi. Question? Well, it all depends on what your goal is for. And whenever you have a beam antenna, it will always look for the azimuth of where the maximum usable frequency will be in the atmosphere, or if you're going straight over, this is VHF. This is just going to be line of sight. So outside of giving a couple of guys that are in the front here a little jilly with RF, there's no reason why it should be bouncing down. It's either that or pointing at the top of the head and it needs some more Rogaine. No, I'm just kidding. Well, what it is for those that have put together an antenna that's been store-bought, there will be insulators that will separate the elements from the boom, which is what the wood is. This is just showing that you don't have to have a metal boom. The only problem that occurs with something that's wood is on a day like today when it rains. If this becomes wet, it's now conductive. Your insulator is conductive and everything else. So water will automatically create an arc. So if you have too much energy that comes across, you will see a situation that occurs and it will arc or short out your antenna and possibly even blow the finals on your radio. So, but for here, it's just a demonstration to show that this does not have to be metal. Your boom does not have to be metal, okay? Wood is a good insulator, but once it's done an arc path through it, it's created carbon. And carbon, as we all know, is a good path for energy to follow on. So once it happens, it's toss it away and do stuff with that, okay? So that's what the whole thing with this is. And I hope you learned a little something from the Yagi demonstration of what goes on. Now, there is a formula that goes on in setting up your elements and all, and it's good for up to having 3 directors, and then the formula changes. That's directors are the ones that are in the front, the shorter ones. And as that goes along, it will take your, where did my mind go? It'll take you, with gain and all through that. So having the multiple directional antenna and with the directors in the front will help you pin down your signal, get into one location, fine tune it. After the 3 elements, you then have the second formula. That's where I was going to, and you have to modify with that. So yes, question. There are different variations of the antennas, and what happens is you'll see like a fishtail that'll come up with multiple on them. What it does is it helps get rid of the amount of energy that's coming from your original driven element, because that's still sending it out in 360 degrees. And instead of just seeing as one plane, it tries to capture a little bit more and a little bit below. And the center of where the 2 of them are, it works the best, still in the line. Yeah, right. It works like in a larger area. Now you'll also see in some antennas where there's like something that resembles like a parabolic dish almost in the back to capture more of the signal. And it's just different ways that people have tried to improve on the basic Yagi, and you can stack these things into multiple layers, but you always have to remember that the object with stacking is to again bring all the energy to a single pinpoint location, and then that way they all multiply that. So if you don't have the real estate, and a lot of people don't have the real estate to put up multi-stacked Yagis, even on VHF and UHF, it's that's what's used. So, but there are different things that can be done. You can have. There are different designs that are out there. Basically, what there is, there are endless manuals and encyclopedias and consortiums and everything else that's just on the theory of antenna design. Okay? And the whole thing is you can get all sorts of stuff to radiate a signal. It's just how efficiently it can. Now you can take various different types of antennas, such as like a Wyndham antenna, which is only one side of a dipole. You have to match or use something that says an artificial counterpoise to make that dipole system work, because if you don't have it as balanced, it's going to be all lopsided. And we're going to show that a little bit in the next section, which is your vertical antennas. You have a question? Each of the directors. They will get progressively shorter, but a lot less noticeable to the eye because of the distances of what they are in the direction that's going on. So it won't be as dramatic as coming from the driven to either the director or from the driven to the reflector. Okay? There was a question over here. Okay, it was rescinded. Yes?
With the Yagi and your design
Okay, on VHF, a basically 19¼ inches is sitting right in the middle of the spectrum. 19 5/8 is your reflector. Okay, and the reason for the two size differences is because anytime that there is an electron flow in any material, what happens is for it to radiate out into space, it's going to reach the end of the material and then hop out into space. So it has to be a little bit shorter than the actual length that is needed, or that would be for the frequency. So it jumps out, comes to free space. That's what you wanted to do. The counterpoise on the other part, you don't want to have signal coming out of, so it has to be the full size, full length. You got that? Okay. So, and that's what we're going to show here in the next thing. We've got a vertical antenna. All right. This is using an SO239, which is the female side to a 259, but this is a panel mount. This is the exact same thing that you would do upon reading your tech manual and saying, okay, how do we make an antenna? And this is what it is. So all I'm doing is I'm just putting this in, and we're going to do the first demonstration showing what happens when you have no radials. Okay, no radial system to do anything with the antenna. Basically, all you're doing is you're shoving your raw energy out the one piece of wire. Now, the whole thing that also occurs is this is, just so everybody is aware of it, this piece here is basically the one side of the dipole. Okay? So that's what we're doing with this. We're working with half of the dipole. And in doing that is where we come up with the next. Always works good to put the coax up to it. And bulb. Here we go. And all I'm doing here. Yes. Yeah. Right. You're pointing at where it is, and you're going with the different stuff. So. Hey, Phil.
How you doing? Well, I'd like to present this to you from the committee.
Okay.
Thank you for your time and effort.
Thank you.
Okay, good job.
All right. So basically what we're going to do now is, hopefully we won't fry too many bulbs. Yeah. Okay, we're now on low power. Okay. We're going to come up to medium. Okay, there we go. Okay, why isn't this one going? We bought this one. As I said, it's always fun. I had another bulb over here. Oh, here it is. And what's the one thing we've already all learned about ham radio? Even more than that. Be prepared. But it's also a hobby that you're always talking to yourself. We are going to do this. We are going to do that. Okay. There we go. All right. Now, I have to be almost up to it to see what's going on. Notice that the energy that's going to the vertical element is very strong. Signal, not so strong. We do know that it's direct, it's going to be, it is definitely vertical, okay? So, what's this telling us? That no matter what direction it's transmitting in, around that we will see energy coming out of it. But it's very, very unhappy. All I'm going to do here, if my finger and index finger will work, is put an element on. Yes. Okay? It's a lot happier. It's more efficient. It's balanced. Okay? The problem is, what do you see as the problem? Goes everywhere. But also notice, I don't know if you can catch it, a little bit directional. Also, my radial is also transmitting. So I have a vertical and a horizontal in this specific configuration. How many here for HF are using something like the MFJ, I forget what the model of it is, where it's got the upright vertical and it's got the one radial that comes out. And they use that for HF as a mounted on the ground. This is, huh? Okay. Well, the Gap Titan, you've got 360-degree radials going around it. A minimum of 3, maybe 4. The more you can put into them, the better it's going to be. And this is what you're looking at right now. It's the same principle, just a different frequency. But if you only have one radial for your radial system, right, for your grounding system, it's going to be very directional. It's following the direction of the radial. Because watch, see it there? And I now turn it 90 degrees on the radial and there's no signal. So what you're doing is you're seeing this type of construction, right? And all my energy is going out this way. And lighting up this element and this element. Okay? Save the microphone. You just saw it, yeah. One was this way and one was this way. So you do have vertical and horizontal. So is that what we want? Not necessarily. We want stuff to go, right? Not to go here and then flat. We want it vertical and have all the radiation coming out of it. So what we're going to do now, and you just slide under there. Come on, be good. Do what I want you to do or not. There you go. With a name like Wenzel, I can talk like this. Okay. See what happened? I'm not losing as much energy coming up through my vertical, but look what's coming out. It's improved. The antenna is happier. And here's the reason why. My radial is no longer a transmitting element. It's now really in a vertical pattern. Okay, now watch. Yep, it's going to have directionality. And remember, directionality is always going to come off the face of your radial system. Okay? As your transmitting is doing the same thing. All right? So your energy is coming off in a vertical plane. It's now vertically polarized. Okay? So that is the efficiency of what goes on. And you can see how much happier the antenna is. I haven't changed anything with power. But the bulb is over 50% brighter than with just the one antenna radial. And with none, it was almost non-existent. Okay? That is the importance of having a radial system. Now, when you're looking at particularly into HF, and they're saying, okay, you got to put in 3 radials, and in the sign of, one up and the others coming out, your antenna, all that's doing is giving you more of an omnidirectional pattern. Because through each of these ground radials that you have, it creates a lobe. So there's a lobe that comes out here, then there's a dead spot, then there's a lobe that comes out here, dead spot, lobe that comes out here, and it's flightening up a little bit here, then it comes back to the other way. And that's what we're going to show now. So here we are again, vertical. Still have nothing horizontal, have nothing, at this range. So we're happy here. And see the bulb? As we come in between, there's a null spot that's in here. So if I follow it out in the arc, there it is. You can see it getting lighter and darker. Okay? Yes?
What does the bottom actually demonstrate? Touch one radial on the bottom.
I'm right on it. That's what your question is, right? So I am seeing stuff that's there. There is a little bit of energy that's emitted. There always is. But it dissipates real fast. Okay? So what have you learned about this right now? The best thing you can do is have a good counterpoise, right, for your antenna system. What you've basically done is this is your 2-meter antenna, again it's in the tech book, that you would put up on top of a pole or a mast or something. Now here's the other interesting thing that occurs. We are at 90 degrees, all right? With an SWR meter hooked up, you could see the pattern that happens is if you take this, because it's not at a 52 ohm impedance, okay? If this was to be bent down to about a 40 or 45 degree angle, is where it will become 50 ohm impedance, okay? You'll see more intensity coming out of your transmitting half. And you will also see a decoupling of the RF that is emitted, that is seen from here, from not going down onto your shield. Okay? Excuse me? No. Right. So that is the thing to be aware of when you make this type of antenna. And why you usually will see your radials on an antenna down around 45, 40 degrees in that range. So it changes the impedance. You're about 62 ohms with it this way, and it brings it down to about 50 ohms. Okay? It's all stuff you didn't even think about, but this is what the efficiencies are. So, and that's with an antenna radial system, particularly on VHF like this, you can put it up in the air. You can put it at the end of a mast, where it's separate from everything else. When you get bigger, like in HF, you got to look at your counterpoises. How can I get a counterpoise? Is it effective for me? Or do I have to stick the antenna in the ground and use the ground as a radial system, or run the 33 feet, the 60 feet, and all for the radials? Again, every single radial that you put up onto the antenna system will reach for that frequency that it is set for, and will be the most efficient for that band, particularly if it's a multi-band antenna. That's no. If you're doing a vertical like this, the more radials you put into it, the more directional. Yes, it'll become better omnidirectional. Okay, but the antenna system will be a lot happier because it's got this stuff. Now, does your radial system have to be the size of your shortest or longest frequency that you want to work with that antenna, if you wanted to make them all the same for it to work right? Anybody got a guess on that? Yeah. Shortest or longest wavelength? Longest.
You need to be there if they
There you go. Remember in the old black and white movies like Frankenstein and Dracula, you had Jacob's Ladder, right? The arc would reach a point that it was equivalent to the frequency that it was being transmitted. When it reached that spot, in other words, the distance between the two rods, it would then jump out into space and be happy, and that's why it would jump out into space. So as the frequencies would change, it would do that. And you just see it climbing up and then coming out to that. Same principle happens with a disc cone antenna. And why a disc cone antenna is usable, again, with omni, no gain or anything, it's only 1-for-1, but it will find multiple frequencies that it will radiate at because you're sending the energy in from the center and it's coming out through the different radials, and it will find what you need. Same thing would happen with your ground plane for a multi-band HF antenna, but it's still the concept. The roof of your car, if you put your antenna in the center of the roof, would use the plane of the metal that is your roof. Okay? Now, if you were to take that vertical antenna and put it on the left rear bumper, right, of the car or of the quarter panel, the stronger point for that antenna to be functioning would be the right front. Because why? Because that's where the most metal is. And that would be the most directional of it. That's why the truckers would put in two antenna systems to get rid of the blind spot from the trailer. So that way they would be in phase of seeing that, and you'd have the two signals coming in. So it's just some basics and stuff. Question? Thought? The longest you can get there. It's the same thing as if you're going to operate with just throwing out a long wire antenna. A long wire antenna is basically half of the dipole. You need something to counteract it, to be the counterpoise on it. So you do the match. For it to be an omni antenna. The ground can be the radio.
ground tends to be the ultimate of length because it's the length of the earth.
Okay.
It will find itself.
No, it will to a certain degree because of the material that the ground is made out of. If you have a lot of iron in the ground, it doesn't have to be mountain with iron ore in it. It could be iron flakes or stuff. Your reflective system will be very good. If you're like here on Long Island and it's very sandy and you're not in water, you got quartz. Quartz is an insulator. Okay. Huh? If you're lucky. Worms like to be in other soil other than sand. Okay. So, but that's basically what goes on. So there's always something that comes into the equation that you can deal with. Now, some of the other things that you can do is with a dipole antenna, particularly if you're looking for space and you can drop the ends of the antenna down, or you can go with a keeping your center conductor straight, and then going with a Z pattern, not exceeding more than a 90-degree angle at any time to shorten your counterpoise. So those are all different things that you can do. Like for my house, for many years, I had an 80-meter dipole, and what I did was from my tower to my front tree, it was straight, and then going from the back, I only had like 40 feet, and I had to do zigzags. So that's the, yes. Well, one last question, then we got to close up. All it does is changes the frequency that you're going to operate on. Remember the equation 468 gives you, over the frequency gives you the length in feet. 236 gives you a quarter wave. That gives you a half wave. So this is a quarter wave. And that's all it is. Okay, because of an interaction, that can be a whole nother hour talk. on the 5/8 and stuff. What I can do is I can talk to you after this because we have to let the next speaker get ready and do what they have to do. Yeah, same thing. Whatever the frequency that you're trying to receive, if you can match it, you'll have a better signal. If not, at least on receiving, you can pick up something with anything. But transmitting, you have to keep your radio happy. You have to keep it at 50 ohms impedance. And if it doesn't see 50 ohm impedance, you've got a very costly thing that happen. That's changing your finals. And everybody knows education is a very expensive process. So I thank everybody for attending today.